Now we will see the theory of linear rational arithmetic. So in this theory, you will handle what kind of constraints and how do we solve them. That's the topic of today's lecture. So in our theory, we have this signature. We will have a plus sign. You have other symbols like 0, 1, 2, other rational numbers you can write, and you can compare, and you can multiply a constant to a variable. For example, you can have this kind of constraints. This will be called, they belong to theory of linear rational arithmetic. There is no greater than equal to in the signature, but we can use this symbol because this is encodable in existing grammar. So maybe try to figure this out, how this is possible. In the linear rational arithmetic, this is how we reason. If you have two linear inequalities known to you, you can take non-negative linear combination and subtract any constant number, and then whatever you get is less than equal to 0. This you can derive from the any given two facts in the linear rational arithmetic. For example, here you have two linear inequalities. First one you multiply with 1, other next one, and divide by 2, and lambda 3 is equal to 1, and then you obtain this linear quantity. Similarly, you can derive contradictions by applying this same technique on three different linear inequalities. You take their three linear combinations and derive the contradiction. The contradiction is represented like this. When you say 0 is less than or equal to -1, this is clearly a false statement. So how do we solve such constraints? If I give you a bunch of linear inequalities, how do you say they are satisfiable or not? Or you can derive a contradiction or not? So most well-known method is simplex, and this is exponential time, and then later on other methods were proposed like ellipsoid method and Karmaker's method. They were far more efficient theoretically. However, the simplex remained to be the staple algorithm that is being used in solving linear rational arithmetic in SMT2 solvers. Next lecture, we will look into the ellipsoid method in Fourier-Motzkin and maybe some other methods to understand why simplex is more efficient than others in the context of SMT solvers. So let's dive into simplex. Simplex is very much algorithmization of the fundamental theorem of linear inequality, and on the surface it may not appear the same, but once you dig deep, you'll realize the simplex is just implementing that theorem. At the very end of this lecture, you find that I'm trying to map the algorithmic representation to the theoretical representation. You can follow that in offline. So what is simplex? Okay, so simplex was originally designed for the linear optimization problems. For example, you want to say that x is constrained to be x less than or equal to b for matrix A and column vector B, and there's a row vector C. So you want to C times x, you want to maximize, okay, given the x satisfy these constraints. So this is classic linear optimization problem, and the question is, how do you maximize? So there is a variation of simplex which is called incremental simplex, and that we are used in check satisfiability. And it turns out that both algorithms are same. So let's see how that is achieved. So let's see how would you do an incremental simplex. Take atoms one by one. Maintain the current assignment that satisfies the atom seen so far. Yeah? So if you have a linear inequalities, and so each linear inequality defines a surface, and they say this area is allowed. So another inequality will say this and this and this. Okay, so they finally form something like some sort of a polygon, which we called polyhedra in an n-dimensional space. And each time we have considered, let's suppose 5 or 6 linear inequalities, so we maintain a current satisfying assignment. Let's suppose this is your current satisfying assignment. Now you get one more linear inequality. Let's suppose this one, which says Cx is less than or equal to delta. So first we get this plane, which is Cx equals to delta, which is this red line. Okay? Now I'm saying Cs is less than or equal to delta. That means in the minus c direction is the allowed area. In this area, you want to find a solution. Now current solution is here. So how do I get there? So what do? In this constraint space, which were already existing, I try to maximize in the direction of minus c. If you do that, so first you go to from this corner to another corner which is closer to this line, then you try to jump to this corner, right? And then you realize when you're crossing this line, this is your right point. Okay, so this is the point where you start satisfying the constraint, so you stop there. And this is how you map a satisfiability problem into optimization problem. Each time a new constraint is introduced, either the current point already satisfies that constraint, or it is we try to move towards that. And the movement happens by visiting corner to corner. Okay, and that's how the incremental simplex operates. So this is a satisfying situation. Let's consider a unsatisfying situation when constraints are written like this. Okay, when after introducing this new constraints which allows this space, and the existing space has no intersection, so therefore the current there's no satisfying assignment. So somehow my algorithm should work in a way that should produce unsatisfiability. So how our algorithm is going to work? It will first try to move closer to this plane. Okay, so first it will may jump to this direction. Okay, then comes here, say okay, have I reached? I say no, still cx is greater than or equal to delta. So okay, fine. Then I will jump one more time and then say okay, so have I reached? And then you'll say, oh, I cannot get closer here because if I go there I get far away. Okay, so it increases the value of cx, and actually I want to decrease the value of c, so I should need to go this direction. There's no way of going there, so therefore I have unsatisfiability. So we get stuck, and then we declare that we have unsatisfiability. The question comes to your mind is what is my unsat code? Which constraints are causing me to be unsatisfiable? So we can easily read off from this. Since this point, you read all the planes which are cutting at this point, which is this guy. So these guys are saying that these two guys are together are saying this point cannot be closer to this plane, and these three planes together are saying that this constraint is unsatisfiable, and you report these three as your unsat code. So this is the intuition behind the incremental simplex. You introduce one atom at a time, maintain the current satisfying assignment. When new one comes, you try to move closer to this new plane. If you cannot reach there, then you have unsatisfiability. So recall that we have four functions that we need to support in the service of assembly solver. First, push. A new atom comes, you should be able to add in your constraint system. Pop, you should be able to remove an atom from your constraint system, and you should be able to report unsat core. So we will see that how the simplex can be used to implement all these three functions.